Hi guys, welcome to Easy Math.
In this video, we are going to discuss about a very important theorem in this topic, that is the fundamental theorem of homomorphism. The statement is, let phi be a homomorphism of G onto G bar with the kernel K, then G over K is isomorphic to G bar. Given phi mapping from G onto G bar be a homomorphism with the kernel K. What is kernel K? We know that kernel K is the set of all x in G such that phi of x is equal to E bar, where E bar is the identity element of G bar, right? You have to prove that G over K is isomorphic to G bar. You have to prove that G over K is isomorphic to G bar. First, what is G over K? G over K is the quotient group, right? Quotient group means set of all distinct right cosets. Right cosets are in the form K. For proving G over K is isomorphic to G bar, first you have to define a mapping psi from G over K to G bar, which is defined by psi of the elements in this G over K, that is quotient group, are in the form of the right cosets, that is Ka. Therefore, psi of Ka is equal to G bar. G bar is the group already we defined, that is phi from G to G bar. The element are in the form of phi of A. Okay. You have to prove that this psi is an isomorphism. You have to prove that this psi is an isomorphism. For that, you have to prove the four conditions. That is, first one, psi is well defined, psi is 1, 1, psi is onto, and psi is homomorphism. First claim, psi is well defined. What is well defined? You have to choose two elements from G over K, from this quotient to G over K, and you have to prove that the element, that is the image, psi of Ka is equal to psi of Kb. You have to assume this and prove this. Okay. Let us choose this Ka is equal to Kb. Then these are the right cosets, right? Therefore, this can be written as A belongs to Kb, or this can be written as B belongs to K also you can write. But I am taking A belongs to Kb. Therefore, A belongs to Kb can be written as A is equal to Kb, where this K belongs to the kernel K, capital K. Now, taking phi on both sides, we are getting phi of A is equal to phi of Kb. Since phi is a homomorphism, this can be written as phi of K into phi of B. Therefore, the elements in K are defined as phi of x is equal to E bar, right? Therefore, phi of K is equal to E bar. Here E bar is the identity element of G bar. Therefore, E bar into phi of B is equal to phi of B. Therefore, phi of A is equal to phi of B. Already we defined the mapping. What is that? Psi of Ka is equal to phi of A. Therefore, phi of A can be written as psi of Ka, and phi of B can be written as psi of Kb. Therefore, psi is well defined. Okay, you are taking Ka is equal to Kb and proved that psi of Ka is equal to psi of Kb. Therefore, psi is well defined. Now, second claim, psi is 1 to 1. What is 1 to 1? Psi of K is equal to psi of Kb implies K is equal to Kb. The converse part of this well defined. For that, we are choosing psi of K is equal to psi of Kb. By the definition of the mapping, psi of Ka and psi of Kb can be written as pi of A and pi of B. Post multiplying pi of B the whole inverse on both sides. Post multiplying pi of B the whole inverse on both sides. Therefore, pi of A into pi of B the whole inverse is equal to pi of B into pi of B the whole inverse, right? Okay, pi of B the whole inverse can be written as pi of B inverse by using the lemma already we proved. Okay. Therefore, pi of A into pi of B inverse is equal to, here pi of B into pi of B the whole inverse can be written as E bar. It's the identity element, right, in the G bar group. Since phi is a homomorphism, this can be written as pi of A into B inverse is equal to E bar. Therefore, this is by using the definition of kernel, AB inverse belongs to the kernel K. This can be written as A belongs to KB. This can be written as Ka is equal to Kb. Already we saw in the well defined, right? Ka is equal to Kb. Therefore, psi is 1 to 1. Okay, psi is 1, 1. Next, third claim is psi is onto. What is onto? A mapping psi from G over K to G bar. Every element of G bar has a pre-image in G over K. That means, let us choose one element from G bar, that is A bar. Since phi is onto, this is given in the statement. There exists an element A belongs to G such that phi of A is equal to A bar. Because already we defined that psi of K is equal to phi of A. Therefore, psi of K is equal to pi of A is equal to A bar. Hence, psi of K is equal to A bar. Therefore, psi is onto. Okay. Next, last claim is psi is a homomorphism. What do we have to prove? That psi of Ka into Kb is equal to psi of Ka into psi of Kb. Therefore, psi of Ka into Kb can be written as psi of Kab. Since by using that lemma, product of the right coset is again a right coset, Ka into Kb can be written as another right coset Kab. Psi of Kab can be defined as pi of Ab, right? Since pi is a homomorphism, this pi of AB can be written as pi of A into pi of B. What is pi of A? Psi of Ka. What is pi of B? Psi of Kb. Therefore, psi of Ka into Kb is equal to psi of Ka into psi of Kb. Hence, psi is a homomorphism. Hence, psi is an isomorphism because it satisfies the four conditions. Psi is well defined, psi is 1, 1, psi is onto, and psi is a homomorphism. Therefore, there exists a isomorphism between G over K to G bar. Hence, G over K is isomorphic to G bar. Hence, the theorem. This is very important theorem.
Thank you for watching. Don't forget to like, share and subscribe. Bye guys.